Welcome back. So let us continue. I hope you had a coffee break. Let us continue with Elena Loukaki. She's going to make, she's from Homeotech, and she's going to present about existing models considering local aspects. So Elena, you have the floor.
Hello, can you hear me?
Yes, we can hear you. Can you open the camera and share your screen?
Yes, just give me a second.
Yeah. Okay, we can also see your.
Can you see my screen?
Yeah, it's okay.
Hello, I'm Elena Loukaki, and I will speak about task 2.5 and existing models considering local aspects. Vegetation biomass is a large store of carbon that can have a direct influence on local, regional, and global climate, particularly on air temperature and humidity. MAIL project focuses on marginal lands in order to classify them into carbon sequestration capacity categories based on innovative approaches. The use of marginal lands as potential carbon sinks contribute to CO2 removals and enhance the agroforestry impact rate in the reduction of greenhouse gases. The purpose of MAIL is to use the techniques of identifications of the marginal lands for their appropriate management in order to implement two major actions: decrease overall CO2 emissions and increase the CO2 sequestration and marginal lands. During task 2.5, an analysis and review of existing methodologies for quantifying carbon sequestration was conducted. The methodologies for quantification carbon sequestration can be divided into two basic categories: direct methodologies and indirect methodologies. Direct methodologies are measurements on field, destructive or non-destructive, the UK method, resource monitoring based on the ISA, and direct carbon flux measurements. Indirect methods are allometric equations and models, remote sensing and GIS, the Ipcc Guidelines, and models and remote sensing in combination. Let's see first the direct measurements, and particularly measurements on field. The destructive method is the most direct method for estimation of above ground biomass and their carbon stocks stored in the forest ecosystems. This method involves harvesting of all trees in the known area and measuring the weight of the different parts of the tree before and after they are oven dried. This method of biomass estimation is limited to a small area or a small sample of trees. Although this method determines the biomass accurately for a particular area, it is time and resource consuming and not applicable for degraded forests containing threatened species. Usually, this method is used for developing biomass equations to be applied for assessing biomass on a larger scale. The non-destructive method estimates the biomass of a tree without felling using an optic dendrometer or climbing on a tree or photographs, and it transforms into biomass with the use of specific coefficient per species. It's applicable for those ecosystems with rare or protected tree species where harvesting is not very practical or feasible. The non-destructive method allows to develop an allometric equation to estimate a tree mass from a few simple measurements and then the application of this equation to the trees in a forest. This method has high accuracy, but in the context of representing a small area. Its main disadvantage is that it is highly cost because it requires many human, equipment, and time resources. According to the UK Forest Research Centre, carbon levels in forestry are accounted through the following direct processes: periodic direct measurements of carbon in forestry stock, and sample-based inventories of carbon accounting. Direct measurements of accounting forest carbon stocks and stock changes include full surveys that include periodic assessment of the growing stock in permanent forest sample plots, plot-based survey where the area is divided into homogeneous stands. Surveys sample plots are put into in stand at random locations and basic assessments are made. and two-stage survey in which assessment in all studs are made while acceptable accuracy and precision is achieved by making plot-based assessments in a sample of stands. Sample-based inventories of carbon accounting is most suitable for estimation of carbon stock and stock changes in very large forest, consisting of collation of stands with a total area of many thousands or even millions of hectares. The essential feature of inventories approach include a statistically based survey of a sample of the total area of the forest, assessment of the species composition, age structure, productive potential, growing stocks, and other features of interest in the sample areas depending on the objectives of the inventory, and analysis of the results for the sample areas to estimate species composition, age structure, productive potential, growing stock, and other features of interest. Let's see the resource monitoring based on the ISA method. Successful large-scale monitoring programs typically incorporate data collected at several spatiotemporal scales, each providing a unique and valuable contribution to the monitoring effort. There are 4 types of monitoring: plot and local scale research, long-term monitoring, spatial extensive surveys, and remotely sensed data. Although these 4 types of monitoring represent different spatial scales, they practically and logistically overlap. Plot and local scale research and monitoring provide detailed information not observable at larger scales. In this type of research, intensive data collections provide information that is essential for developing a better understanding of carbon cycling process. This understanding enables the continued improvement of ecosystem models used to calculate carbon sequestration and greenhouse gases fluxes. Long-term monitoring provides trend information not observable by other means. Spatial extensive surveys provide the means to assess variability across ecosystems and provides estimates of population parameters for regions of interest. It provides data at regional to national scales that can be used to evaluate how variables change in response to natural or human-related stressors. A key benefit of spatial extensive surveys is that the data can be merged with spatial continuous national land use and land cover data, and statistical relations can be developed that permit model estimates of greenhouse gases flux at sites not directly measured. And remotely sensed data permit observation and assessment at regional to global scales. This data must be synthesized into a form that permits quantification over the spatial extent of the monitored area and analysis of change with time. This data is essential for regional efforts, such as mapping and tracking changes in land cover and land use, and evaluate ecosystem disturbances caused by storms, insects, or fire. This method sampling is needed not only for area estimation, but also for estimating the state of carbon stocks and emissions and removals of greenhouse gases. A basis for this assessment of variables such as tree biomass and soil carbon is made on the plots. Direct carbon flux measurements. This approach directly measures the net flow of carbon into or out of the forest. The measurements are made continuously from a tower above the canopy. In the picture, you can see a flux tower. The advantage of the flux-based approach is that a net ecosystem flux is measured accounting all carbon plots, including deadwood and litter and other fractions which prove difficult to measure using stock change methods. This method has high accuracy, but represents a small area where the flux tower is installed. The main disadvantage is that it has high cost due to the installation and maintenance of the flux towers. Let's go to the indirect methods. First, we have allometric equations and predictive models. With this method, variables such as tree biomass and soil carbon content are assessed through deducing quantity using models based on correlated variables. Simulation models use existing data and knowledge of forest growth and biomass production to create projections or scenarios of biomass production and carbon sequestration in the future under different forest management practices. The accuracy depends on the availability of data that are used as input for a specific sample area. The application of the model-based approach involves defining the area and the breakdown of this area into homogeneous units, stands in terms of tree species composition, age classes, tree growth rates, stand management regimes. The main advantage of this method is that it is cost-effective. The use of remote sensing and GIS. This method is used to obtain information about an area of interest that is difficult to access or even inaccessible. It's realistic and cost-effective. The data are useful for mapping and monitoring vegetation, land cover, and land use change in this method. Also, forest carbon stocks can be evaluated using remote sensing technology. There are 3 remote sensing technologies that are especially promising for obtaining data that can contribute to improve biomass estimates. Long wavelength radar instruments have proved to be useful for estimating and mapping biomass of several forest biomes. Urban LIDAR system and polarimetric second interferometry that consists indirect method to measure forest height and apply local or regional allometric relationships to estimate biomass, and optic data such as Landsat, ETM, MODIS, MERIS, and SPOT. The Ipcc Guidelines. In 2006, the Ipcc published guidelines for agriculture, forestry, and other land uses that define 3 tiers, basically 3 methods for assessing and reporting greenhouse gases emissions. First of all, we have Tier 1. Tier 1 is a basic method that uses default values by land use change type, and is most suitable for nations with limited inventory and remote sensing capabilities. Spatially coordinated default data are used in this method that are based on globally available data. The methods involve several simplifying assumptions, and the default values of the parameters are taken from the Ipcc guidelines. It is a simple first-order approach with large uncertainties. Tier 2 is based on inventory and bookkeeping, and it is used where country-specific conditions and estimates of the activity data and emissions removal factors are available. It is country or region-specific values for the general defaults are used, and more disaggregated activity data. It is more accurate approach than Tier 1 and has relatively smaller uncertainties. And Tier 3 is based on the inventory and process-based models. It includes methods that represent more demanding technical capabilities, accuracy, and data requirements. Detailed modeling and inventory measurement systems data at a greater resolution are used. This method is heavily depends on remote sensing. It is a higher order method than the previous 2 and has lower uncertainties. The selected method for male. For the male project, the Ipcc method Tier 1 was selected. Direct methods were excluded for measuring carbon sequestration in male project, as sampling procedures cannot be performed given the time frame and resource conditions of the project. Tier 1 was selected because the needs of input data may be easily assessed from already existing European or global datasets. The Tier 1 method is a cost-effective approach for biomass and carbon mapping over large geographical regions where gaps in accurate biomass information exist. This method is considered appropriate for continental studies such as at European level. The knowledge gained through Task 2.5 was used in Task 0.4 quantification of carbon sequestration capacity in marginal lands and Task 4.3 estimation of carbon stock in forest products. Thank you for your attention.
Thank you, Elena, for your presentation. And now I would like to call to the stand Mr. Janer Amin from IAPG, who is going to present about the estimation of biomass volume at low productivity mountains and semi-mountainous marginal lands. So, Janer, you have the floor. Just unmute your microphone.
Thank you very much. Yes, I just noticed. Yes. Can you hear me now?
Yeah, everything's okay. You can continue.
Yeah, thank you very much. I will be presenting a summary of the several different studies we conducted on the topic of estimation of above ground biomass in marginal lands. This is a collaborative work between many people in EIBG, and I will be doing a summary of the key findings. In fact, there are three distinct studies we conducted. First study we did was a general exploratory machine learning approach, where we investigated a list of machine learning methods to try to see whether there is a specific method which is more or less suitable for the particular case study. And for that one, we focused on purely optical data from Sentinel-2. The second method was based on SAR data, radar data, Sentinel-1, and it was based on a physically based approach, so inverting physically based model definitions. And the third study we conducted was a fusion between SAR and optical, and coming back to the machine learning approach. So we basically essentially combined optical and SAR data as a predictor variables and investigated whether we have improved prediction from this combination. So starting with the first one, the exploratory machine learning approach, it was a quite significant study which had the goal to identify, as I said, whether there is some method from the big list of machine learning approaches which is most suitable. And on the right side, you can see the top 1/3 is the data preparation, and then we go through the different steps which are typical for a classification study. The first one and related to our question was whether there is a best performing feature selection method. Very often in classification or machine learning studies, you have a lot of features, and one tries to minimize the number of features and make the model more robust. So we try to find out whether one of those feature selection methods has an advantage over the others. And as a byproduct of that, we also wanted to identify which predictors are more relevant for biomass estimation, which is giving us a domain-specific insight on the future, on predictors we have to select for future studies. After that, we went to apply several different machine learning methods and try to find out which one is better suited. Again, you can see starting from a more simple random forest towards artificial neural networks. Following that, after building all that models, as you know, every model has a certain set of parameters which can be played with and fine-tuned to increase the model performance. And we try to find out also which of those fine-tuning methods are whether there is one particular one which is more appropriate. And finally, after having built the model, we wanted to see the specific impact of the predictor variables to the model, so to gain some insights in the model. Going very quickly through the data preparation, we had field data from the University of Valencia in a study site in Spain with above ground biomass estimations. As I said, we used Sentinel-2 data from, we took two different seasons, a summer and autumn image, to also check the performance suitability of different seasonality in as a predictor variables, and all this data was aligned and converted into raster. And at the end, you can see we have predictor variables from 3 different distinct groups of variables. So one related to reflectance, vegetation reflectance, one related to biophysical parameters such as LAI and fraction of APAR, and another set of parameters was the contextual predictors, the variability in the surroundings of the plot, let's say. So going straight to results on the first part, whether there is a future selection method which can minimize, which is useful to minimize the future space, we actually found out that though the methods we used, maybe a little bit background on the methods. All methods are trying to compare what is the performance of the model when one of the variables is excluded or not, and they measure this by the decrease in either impurity or accuracy. And we found that there is no single feature selection method which performs better. And as I said, a byproduct of this analysis would be a ranking of the most important features, which I show here just an excerpt of one of those rankings based on mean decrease in accuracy, and a summary of that importance. We ranked each the features based on its importance for each feature selection method. We checked what is the ranking of the methods, and we summarized everything. And it is noticeable that summer, and it's kind of logical, summer months features obtained from the summer months are there's a tendency for selection of those type of features, and features related to biophysical parameters are also very often selected. And also we included the elevation as a predictor variable, which was also very often ranked in the higher 1/3 of the future space. And I'll come back to this when we try to interpret the results more closely. In terms of the different models we selected, you can see the summary graph of the predictions here, and root mean square error is moving in the high 40s, given the fact that this is the average plot above ground biomass was around 85 to 90, 100 tons per hectare. That means that in percentage wise, we have a root mean square about 40%, which is not the best performance. And we found that before hyperparameter fine tuning, meaning before adjusting the parameters so that we get the highest performance, the neural network was the best performers from the models. But after tuning parameters, the gradient boosting method yielded the highest performance. So here the graph shows the before tuning the parameters. That's why actually the neural network is the best performer on the graph. And among the methods which can be used to tune parameter space, we tested several ones, such as the grid-based method, where all the possible combinations are being tested, and some more optimized methods. And we found that the Bayesian search, which is a method which doesn't go throughout all the possible combinations, because you can imagine if you have many parameters, this creates a enormous parameter space which must be searched. The Bayesian search informs itself from the parameter space and highly reduces the time needed to search for the best parameters. So in this method might not be leading to the best parameter space, but the gains in computation power, computation time are very, very significant, so it must be considered. Finally, this is how the map looks with the gradient boosting method, and as I said, the mean above ground biomass was around 80 tons per hectare. And finally, going towards the insights from the model, we've identified 3 types of impact on the model. We have features which kind of are positively correlated with the model output, meaning increase in the value of the input feature leads to increase in the model output. And those are features related to biophysical parameters, which is logical. The more chlorophyll we have, typically the more biomass there is. Conversely, there are also features which have the opposite effect. So increasing the value of the input leads to decrease in biomass. And a good example to interpret to understand is the elevation. As we increase elevation, typically we have lowering of biomass, and then we have a big group of input variables. We don't see clear visual pattern, and this also relates to the problem of dimensionality and the quality of data and noise. Now I'm jumping quickly to the second study, which was investigation of SAR data, Sentinel-1, and its applicability for biomass estimation. And in opposite to the previous study, which was based on machine learning, this one is based on purely physically based approach. There are several methods to estimate biomass or volume from SAR data, and they're based on the backscatter or on the interferometric coherence. And we tested from the backscatter domain the water cloud model. From the interferometric coherency, we tested one interferometric coherence data model, and there is a combination between those 2 models, which is the simplified interferometric water cloud model. A little bit more detail on those 3 methods. Essentially, volume is a function of backscatter, and in this equation, there is one parameter which is unknown, and it's a constant. It's a parameter which must be fitted, and the coherence method looks very similar. Just instead of backscatter, we make use of the coherence data, and the third method is a combination of those 2, and this is the straight formulation, which is used for coherence, but this can be inverted this can be inverted for volume. So essentially, out of this formulation, again, formulation for volume can be extracted, and then again, there is the beta parameter which must be fitted. Straight to the results, we have very low accuracies. For the water cloud model, you can see the RMSEs moving in the higher 70%, 80%. And yeah, this is a very simplistic model which has only one parameter which can be modified, and this is the reason for the relatively low results. Coherence method slightly better, and especially in the lower above ground values, but the notorious underprediction in the highest values are very much observable. And also observable is that it depends on the tree species, and very similar results to for the combined model. Results in the 50s% for by the way, I forgot to mention that the two graphs, the difference between the two graphs is the input, whether we are which polarization we are using for the estimation of coherence. And yeah. As a summary for the SAR estimation, there is a better performance when we combine several polarizations and multi-looking approach, and yeah, ascending and descending orbits allow to eliminate some of the topographic effects, and yeah, environmental factors might also affect the results. And final third of this presentation is about the final approach, which is then we are coming back again to a machine learning approach. Whereas in the first one, we were exploring a list of different machine learning methods. In this one, we are choosing only one, the random forest method, and we are investigating the whether the fusion between SAR and optical data can improve the prediction. And similarly to that, we have a very typical data pre-processing chain where we collect all the data. As I said, we have the Sentinel-1, Sentinel-2, and another SAR sensor data from another SAR sensor. And everything then it's fed to a random forest model. The similar optimization steps have been performed. Again, feature selection and minimization of the feature space was performed. And there was several regional models and one global model, which basically combines the data from all the study sites. In terms of study sites, we have several of the study sites from the Mayo project, but there was also data coming from different other locations, a collaboration from the master student who was doing this work. This is again a summary of the data which was used, Sentinel-1, 2, and ALOS, and some auxiliary data from land cover, classification to climatic variables, and also, again, elevation. At the end, there were these 25 features, reflectance data, different polarizations from the SAR sensors, and some of the bioclimatic variables, and then directly to results. We are again moving in terms of RMSC percentage in the range of 40s, and we see that locally we have a better estimation because of course the local model is trained and predicts on a very local scale. But when we combine the data from all the ecosystems, which are quite different, in fact, we have a lowering of the accuracy. So probably a conclusion based of that is a very difficult. It's almost impossible to create a one unified machine learning model which is applicable for every scenario, and more localized models based on geographical regions are to be considered. Again, another conclusion was that because we tested also the different whether we tested also purely SAR based model, purely optical based model on splitting the data between from using only the SAR or only the optical data to create the same model, and essentially data fusion results were always the best. And notoriously, again, there was an over prediction in the lower values and under prediction in the highest values, as we saw in the first case. With that, I would like to thank you for your attention.
Thank you for the presentation, Janer. So there are no questions currently, so we can go ahead with the next presentation by Fernando Bezares Sanfilip and Eleftheris Mistekidis, which is about the classification of marginal lands in carbon sequestration capacity groups. So Fernando, you have the floor.
Thank you very much.
Janer, can you stop sharing the screen?
I'm not sure how to do that. New share. There is a new share.
Maybe if I just like say to share my screen.
Yes, that's it.
Then...
I think that we can.
Okay. Can you see my screen?
Yeah, everything's okay. You can go ahead.
Let me see. Okay. So welcome everybody. Thank you for the presentation before, Janer. And now I would like to introduce my presentation. I'm Fernando Bezares. I'm an engineer in FESEFOR. And today I'm talking about the task 2.7, which I coordinated, but the part that I'm presenting right now was carried out by Julia Molis, that she is not present today, but I like to point this out. And we're presenting the classification in carbon sequestration capacity groups. So first I'll introduce my part, and in the next part, Eleftheris will explain his. So the objectives defined in this task were, first of all, classifying carbon sequestration capacity groups in Europe and in marginal lands. For this, we wanted to identify and develop indicators to assist the estimation of these current carbon sequestration groups within given areas. So, as I said, there were two main scales that we wanted to operate, and one is the pilot sites, and the other is in the European scale. So the part that I'm going to present is the pilot site analysis in precisely the Sierra de Espadan. And the European scale is going to be presented by Eleftheris. So before jumping into the description of the carbon sequestration groups, I think it's important to point out several definitions to be based on the same ground. So first of all, we're going to see what is the carbon sequestration, then what is the current carbon sequestration, the carbon carrying capacity of a system, and finally, we will introduce the carbon sequestration capacity concept. So first of all, the carbon sequestration is a natural process involving the capture of carbon dioxide from the atmosphere and its long-term storage into three major carbon pools. Namely, there are the oceanic, then as a terrestrial, and the geological pool. And the International Panel on Climate Change divides the terrestrial pool in 5 main reservoirs, and those are the above ground biomass, which is comprised mainly on the trunk, leaves, boughs, bogs, and branches. Then is the below ground biomass, which are mainly the roots, the root system of the trees. Then is the litter, or the fallen leaves, and the woody debris. These are dead wood on the ground. And finally is the soil organic matter in the system. So with this, we could say that the carbon sequestrated within the terrestrial pool is the sum of the amounts of carbon in the vegetation, biomass, and soil. The next concept that we need to introduce is the current carbon sequestration, which, as it says, is the carbon by itself, by the definition, is a carbon storage in a given moment, or right now, namely in a forested area, the carbon current sequestration can be defined as the amount of carbon stored in the forest biomass in the moment of the forest inventory. Typically, we say current, but we are constrained by when this forest inventory was carried out. So typically is the last forest inventory. And in order to transform the carbon into the biomass into carbon, and normally we assume that is the 50% of the content within the biomass. The next concept is the carbon carrying capacity. This is defined as the amount of carbon stored in a forest in a state of dynamic equilibrium or excluding anthropogenic disturbances. This state of saturation is reached when the forest reaches a full growth, or namely an old growth forest. In ecology as well, we can call them climatic ecosystems. And well, this definition was defined by Keith. So why have we talked about these different type of carbon sequestrations, carbon carrying capacity, current carbon sequestration? Is because carbon sequestration capacity is defined based on the concept that we introduced before. So this is the maximum potential quantity of carbon confinement for forest in the moment being, and is estimated subtracting the current carbon sequestration to the current carbon carrying capacity, carbon carrying capacity. Sorry, too many C's, and is defined by this simple formula. So now I will jump into the more practical stuff, or more visual. And here, first we defined, or we calculated the two components of the equation separately, and then we calculated the carbon sequestration capacity groups. So in order to calculate the current carbon sequestration, we calculated for the Sierra de Espadán because we had ground data available provided by the university, the Polytechnical University of Valencia. And this data was estimated by Julia through using LiDAR and Sentinel-2 data, and it was estimated only for the above ground biomass. She applied machine learning algorithms, and the logic that this carbon estimation was, how this carbon estimation was assessed, it was already presented by Janner. So with the output of this analysis, we got the map that we can see in the screen. And next element that we need to know is what is the carbon carrying capacity, or let's say the maximum potential carbon that we could have. And for this exercise, we imported the results from the task 4.2, which it had as a goal to quantify this potential carbon sequestered in a marginal land area, where somebody were to, if somebody were to make a reforestation plan there. And these carbon sequestration values were based on locally calibrated allometric equations and yield tables. So for this location, in Sierra de Espadán, we got 2 marginal land classes, and using a selection of species that later on will be explained by Janner in the quantification of carbon sequestration of the marginal land presentation, they obtained these 2 values. So finally, with this data, with knowing how much carbon we have in each marginal land, or in this future afforested area, or this potential, minus what we have in the area, we got these carbon sequestration capacity groups defined by the ranks that you can see in the photograph. So the blue lands, or the blue marginal lands, correspond to high suitability for plantation lands. Let's say the marginal lands with higher potentiality to incorporate carbon, and the red ones are the lands with the lowest suitability for plantation. And of course the group 3 are the the areas that they are not considered marginal. So in spite that we have in the map of the current carbon sequestration, we have, of course, carbon sequestration values. They are applied to all the area, but we are only interested in the ones on the marginal lands. These are the references that I used to define these concepts that were introduced before. And without further ado, I would like to give the floor to my colleague Lefteris, that he will introduce the European analysis for the marginal lands.
Hello again. Following the presentation by Fernando, I will present you the second part of task 2.7, which is about European scale. For this part of the task, a new approach was developed, as it wouldn't be possible to apply the same methodology as previously presented by Fernando, due to the extent of the study area covering the whole Europe and the time frame of the task. Field measurements or remote sensing wouldn't be feasible. Regarding this, we applied a methodology based on multi-criteria GIS analysis with suitable species. For the implementation of the task, due to the extent, the size and resolution of the data, as well as for compatibility with the mail geoportal, we worked on Google Earth Engine, where we also developed a tool to be included in decision support system. For the implementation of the task, we used EFI 3-species maps, which describes the spatial distribution of 23 species groups at 1 by 1 kilometer resolution, based on ICP Forest Level 1 plot data combined with National Forest Inventory data of 18 countries. We also used S2GLC land cover map of Europe, one of the most detailed pan-European land cover products produced using automatic classification approach and Sentinel-2 image, and composed of 13 land cover classes with 10-meter spatial resolution. And also we used global above ground and below ground biomass carbon density maps for year 2010, which provide an estimate in megagrams of carbon biomass per hectare in 300 meter square pixel resolution. In order to estimate the carbon sequestration capacity for marginal lands and classify into groups, it is crucial to estimate potential suitable species for afforestation and their above ground biomass carbon. As far as there are areas with no data in the EFI 3-species maps, like Cyprus and some other islands, we processed 3-species maps with S2GLC data to produce a 3-species map for all European forested areas. Also, by combining the above-ground biomass carbon density map with vegetation map, we calculated above-ground biomass carbon for 3 species. For each marginal land, as being calculated on task 2.3, we assigned the most frequent species from neighbor forested areas, both dominant 1 and dominant 2 species. These species are adapted to the ecological and climatological conditions, and therefore are considered to be the most suitable for afforestation projects. For sure, this is just a suggestion and by no means does not replace field observations or further analysis. Also, for each marginal land, we assigned those species above ground biomass carbon values. In this slide, we can see a more detailed workflow for creating a layer with vegetation for whole European cover. 3-species maps for European forest consist of 23 species rasters with values from 0 to 100, which is the percentage share of the respective 3 species from land area. These rasters, reclassified by 5% interval, combined in one raster and processed in order to detect the dominant 1 and dominant 2 species. Finally, we produced 4 single band rasters, dominant 1, dominant 2 species, and their percents. In order to cover all forested areas, we used focal mode, a morphological operation implemented on Google Earth Engine, like a majority function, configured and applied it in ranges from 500 meters to 30 kilometers, both for dominant 1 and dominant 2 species. Because of some areas with no data from EFI 3 species maps, we used S2GLC land cover map. Firstly, we masked 3 cover values, broadleaves and conifers, and then mosaicing with dominant 1 species to complete the layer for all European forested areas. Regarding the process of above-ground biomass carbon density map with dominant 1 and dominant 2 species data, we used the same algorithm as well by applying focal mode in ranges from 500 meters to 30 kilometers and then computing the above-ground biomass carbon density mean. For the estimation of carbon sequestration capacity, we created a formula in which we multiply the following variables: above-ground biomass carbon mean, which is the mean value from dominant 1 and dominant 2 species, productivity value of marginal lands as calculated on task 2.3, and weight factor 70%, which we consider to be the upper limit of a marginal land after being afforested compared to neighbor forested areas, because marginal lands by default have productivity restrictions. Marginal lands were classified in carbon sequestration capacity groups with 2010 year as a reference, and in this frame, each group does not represent the maximum carbon stock that can be obtained. It is more appropriate to say that it helps us to understand the relative interconnections between groups. Carbon sequestration capacity, as well the groups, may change from year to year due to various reasons and factors. Classification in the carbon sequestration capacity groups was done by manually defining classes ranges in such a way so each class to cover approximately the same area across Europe, with the exception of higher and lower sequestration groups, Group A and Group B respectively. Group A represents higher sequestration marginal lands covering 5% of Europe's total marginal lands, and on the other side, Group B represents lower sequestration marginal lands covering 31% of Europe's marginal lands. Finally, we developed a tool that will be accommodated to the platform into the decision support system. The tool provides the options to users to select an area by drawing a polygon or insert a geometry from file, and then displays information regarding carbon sequestration capacity groups at potential suitable species for afforestation based on presence frequency in the neighbor forested areas and ranked according to dominance. In each pie chart, the results illustrate the relationship between percentages of the whole area of interest of the stakeholder. The purpose of the tool is to provide a general overview regarding carbon sequestration capacity groups and to suggest potential suitable species for afforestation. In no case, the results from the tool can replace a further study such as the one reported for the pilot site level, in which a more detailed analysis was performed and based on field data. Thank you for your attention.
Thank you, Lefteris and Fernando, for your presentations. I would like now to call to the stand Michael Kurpinski and Fernando Bezares-Sanfelipe that they will present the web application for marginal land management. So, Michael, you have the floor.
Thank you for introduction, Harry. Can you hear me well and see the, oh, 1 second, first slide. Can you hear me well and see the presentation?
Yeah, we can see the presentation, Michael.
Great. So I have an honor to present the web application for marginal lands management, which is developed within our project. And the presentation will be done in the first part by me and in the second by Fernando. I work in Space Research Center of the Polish Academy of Sciences as geospatial analyst. And I would like to thank to our whole development team, which was involved in preparation of this tool, this website, because actually what we show here is the result of many different tasks which were prepared, developed, and implemented by various people. So I would like to mention here Marek, Jesus, Fernando, Pablo, Zoe, Yorgos, Janner, Lefteris, Francisco, and probably I should list also other secondaries and coordinators which also prepared something what in result will be shown in our website. This also shows that all of our partners, all secondaries from each partner were involved in preparation of this final web portal. The objectives which we were following to prepare it were firstly to find the optimum, the best way to present the most interesting, the most useful outcomes and results of our project. Then we wanted to provide the users the interface which will easily let them interact and analyze, play with the maps and results which we developed. And also we wanted to allow for some expert or semi-expert analysis of potential CO2 sequestration related to marginal lands in Europe. We decided to do it as a website, actually geoportal, and we called it Mail Map Portal. The requirements which we had to follow preparing this were, firstly, we wanted to have the maps which will cover the whole Europe. Also, we wanted to include some figures, some plots, some results of analysis which will give us the quantitative way, in the quantitative way, the values of parameters or scenarios which we will try to analyze in our tool. And we also wanted to prepare the tool which would allow us to generate some report with the summary of performed analysis, which we can share with and discuss with other users or stakeholders. And moreover, we wanted the platform which will be capable to analyze huge amount of data, because we are working on the whole area of EU with many different databases, as already were mentioned, for example, by Maria in the morning. And because the spatial resolution of the highest of them was actually 10 by 10 meter by pixel. So what was the solution which we have chosen? Already Lefteris mentioned that we decided to use Google Earth Engine. First of all, it already contains a lot of data which we need, which we analyze often on the fly, as in the algorithm presented by Yorgos. Secondly, it allows to prepare the tools where user can interact with the data, can generate the plots, the results, modify the maps which he can see. And this is possible using this platform. And for now, it's for free. Let's hope it will stay this way. So this is the landing page of our mail map portal. And basically, we can say that we have actually two main parts of this website. The first one is related with marginal lands mapping, and the second one was focused on decision support system related to the carbon analysis, carbon predictions, carbon calculations. And I will show you firstly the mapping tools, and Fernando in the second part will give you more details about decision support system. The products and layers which are available in our portal are firstly the marginal lands productivity. It's the result of task 2.3. You may remember from the presentation of Maria from the morning that we performed the huge analysis of databases for Europe. We have compared them, analyzed which parameters are useful for identification of marginal lands. And we implemented it for the whole Europe, creating the stable layer indicated which areas are potentially marginal lands and which not. So this product is presented in our web portal on the name called Marginal Lands Productivity. The second type of layer which is visible is called Marginal Land Productivity Classes. And they were also mentioned in the morning by Maria. We have three classes. Class 1 with the high suitability for plantation or afforestation programs. Class 2 moderate suitability, and Class 3 the low suitability. There is also another part which is more dynamic and will allow for multi-temporal analysis on or monitoring of marginal lands areas. I will focus now on two first parts, and the multi-temporal analysis will be showed in the afternoon by Marta Milczarek. This is example how marginal lands productivity layer looks like. Here we can see that marginal lands are indicated in this purple cyan color, which has values from 0 to 100, where 100 is the highest productivity, 0 is the lowest. And the first thing is that we present this map. Everyone can navigate and analyze any area in Europe to see where are these potential marginal lands. But we also wanted to give some flexibility to the user that he can modify some parameters. Generally, we have two types of marginal lands productivity. First one, which we can call base map, is the result of our analysis performed in task 2.3 and presented by Maria. And the other source of marginal lands area is the enhanced map, which is based on satellite image analysis, and it was presented in the morning by Yorgos. The base map is calculated, prepared only for one period of time for the years 2017-18. In the enhanced map, user can define for what date he wants to see the extent of marginal lands. Base map, all the analysis is based on the existing databases. These databases usually are obtained from EO data, but enhanced map is using directly the analysis of Copernicus Sentinel-1 and Sentinel-2 satellite images. In our base map, we perform the analysis for the whole Europe, and we present the results in our portal. And in case of enhanced map, the analyses which are performed on fly can be done only for the regions because it requires really huge amount of data. And we wanted the user to have the flexibility to choose the days, choose the area, and it influenced the results. So they have to be generated quickly. That's why we limited the area of interest to the regions. What other flexibility the users have using our tool? In case of marginal lands productivity, they can, for example, exclude land cover classes. As Maria mentioned, in the hard thresholds, we have already excluded some of the land use land cover classes, but maybe for some reason, user would like to actually see what are the potential marginal lands within protected areas. So using this feature, he can add them to the potential area of interest. Another thing is the selection of productivity range. By default, we can see all potential marginal lands. So the ranges of various values are from 0 to 100, but the user can, for example, say that he's interested only in the moderate and high suitability areas, and that he wants to see the values only from 50 to 100%. And the third option related to this layer is modification of factors importance. This is related with the soft constraints, which were presented by Maria, and they are grouped in three main categories. The first related to the terrain and soil, second to the sustainability, and the third one with productivity. Within each of these groups, there is a number of parameters, and for each of them, in task 2.3, we have performed the research, the literature review, the analysis of usability of these parameters, and we have ranked each of them accordingly to our study. Generally, we advise to use our parameters, but to provide some options to modify it, we allow users to modify these ranks, but we advise that it should be followed by the knowledge or research for the specific region where the user, for example, knows that in this specific area, this parameter should have actually more importance than the other. Second layer, which is called productivity classes, allows us to actually modify the division, how we want to classify our productivity into three classes. We can do it in 4 ways, using or equal division or the percentiles, or user can input manually the thresholds, how to divide our productivity values into 3 categories. And the second part, and I give the floor to Fernando, who will show the second part.
Hello again, everyone. Thank you, Michal, for the presentation and for introducing our tool. And let me see if I can select here. Share. Okay. Can you all see the screen?
Yes.
Hello. Okay. Thanks. Perfect. So as Michal has introduced before, greatly, we have a decision support system for selecting marginal lands suitable for reforestation, and again we have embedded all the system in the fabulous Google Earth engine. And first of all, I would like to quickly refresh the structure that we have. So in the tool we have the main tools that Michal has introduced and explained, based on a tool to exclude the regions by the type of land cover. Then we can exclude the regions by productivity values, which will be further explained later on in another presentation. Then a factor importance selection. And finally, with all this information that we have embedded in the system and in the tool, we classify the productivity within 3 classes. And parallelly, we have the decision super system. The main difference with the main tools is that the decision super system is targeted to work in a local scale, whereas the main tools operate for the whole European scale. So in this sense, the decision super system will have an area selection tool and identification of the marginal lands feature, which can select it in 2 ways: distance filters and analysis tools, which comprise mainly carbon analysis tools that I will further explain. So the main workflow of the toolbox of our app is on one branch, the main tools, and on the other branch, the decision support system tools. So firstly, the user, when it loads in the system, will have to select an area. Then this area, and within this area, they have to select what type of classification do they want to use for the marginal land identification. So one is the European classification, which is what Michal presented, and the other is the enhanced classification, which is what Yorgos presented before. And once we have identified this reforestation, with this identification of the marginal lands, we have to decide what type of reforestation we have to carry out in our area. And depending on this, we're going to have two different types of filters to the areas that I will later on explain, based on the feasibility of the reforestation and on the biodiversity filters. These distance filters are basically, the user is basically going to indicate how far do they want to perform the reforestation based on distances to these land areas. And once we have classified identified these areas, and we have masked the marginal lands according to the distances, we have the marginal lands identified in order to apply the analysis tools, which are the carbon calculator, carbon predictor, and a forestation cost calculator. So the first step, as I already said, is defining the area of interest. And how are we going to do it? So we can do it using a NAT3 level layer with NAT3 level units, which are represented in the GAU level 2 layer. This is an example of France in Les Ardennes, is a region in the north of France. Or we can use it by a user-defined polygon, which they can draw as many as they want in order to define their study area. It doesn't have to be a unique polygon. Another feature that we have that I forgot to introduce here is that we can introduce external information. Let's say you have your own already defined polygons, and there are too many polygons, or your plots, and you don't want to draw them by hand. So you can import it as a GeoJSON string, and the system will plot it for you. This is the menu that we have for the selection of the areas. You can first select your country, and then in the box in the you select widget before, where it says now all regions, you will have displayed all the NAT3 areas. And in case that you don't have a NAT3 areas in your country, they will deploy the NAT2 level. Or parallelly, we can have you can draw your area. If you select the area, then you will have the menu there to introduce as well you import your GeoJSON as well. The other feature is the identification of the marginal lands. One is the European classification that Michal introduced, and the other is the enhanced classification, which is where you can find actually in the DSS is the only place where you can find the marginal land enhanced classification menu, because this is thought and designed to work in a local scale. So for as Yorgos has already introduced and explained perfectly all the tool, but I'm going to quickly remember how we can how this works, because it's a kind of a special feature introduced in the DSS. In the left corner, you can see down left corner, you can see what this identification method would look like. It's just a selecting device that will tell you which type of classification you want. And in case of selecting the enhanced classification, the user will have to select 2 dates. So going to the enhanced classification and not getting too much in the details. And if I say something wrong, please, Georgios, correct me. First, we have a European-based training layer where it's fitted for 2017. And here we're going to obtain variables for Sentinel-1 and Sentinel-2 that are going to describe how our marginal lands look at this point. The variables that we have for Sentinel-1 are mainly VV and VH variables for the months of April, June, and October. And then for the Sentinel-2, we have they have run indicators, SAVI, NDVI, and NDTI indicators, along with a harmonic model to extract the phase and the amplitude. Once this is run, the user can get into the system for the classification and specify in a date. They are going to create another, they are going to replicate the variables that we have seen just right now, but instead for 2017, they can do it for 2019 up to 2021. There's a limitation of a 2-year interval that the application blocks if you want to do it for less than 1 year. Otherwise, the classification wouldn't run. So in this part, the user selects one date, and we will obtain the variables that we mentioned before. And on the other hand, the classification works as Jorgos explained, training classes to obtain the reference data for the marginal land distribution through a stratified random sampling that then is overlapped and over the European base map that we saw before, which contains the variables for 2017, and then they applied a random forest classifier. So once we have identified our marginal lands in whatever under whatever methodology, then we apply the distance filters. So what is exactly the distance filters? As I quickly introduced before, the distance filters are is a mask based on distances that the user is going to define in specifying threshold to key land cover areas. So within these filters, we have two types of filters: the feasibility filters, which are the ones that condition or limit the success of the reforestation, which is like the distance to crops, distance to roads, or distance to urban areas. And then we have the biodiversity filters. The biodiversity filters are mainly and uniquely used for protective types of reforestations where we understand that it's not that important, the economic value of the reforestation, but we are more interested in how this reforestation is going to connect with other forest patches or with protected areas. And then again, it calculates the distance to a target forest or a target protected area. This would be the look of how we can select the type of reforestation and the distances to our key areas. On the left, we can see the productive filters, and on the right, the protective filters. So these distances, they have a limitation of 5,000 meters because if we run it in a lower resolution, let's say 1,000 meters, then there will be some areas that we cannot compute at certain zooms. So, and also maybe the user is interested in having at least 5 kilometers of distance to a target area, unless maybe it's going to condition the search of the interest areas. This distance filter, they have two modes. One is what is set by default, and is that whenever we set a distance to a key area, let's say forest, the tool is assuming that distance is closer than the pixel. So we select the pixel and we say we want 500 meters from that pixel. So all the area that is close to 500 meters is going to be selected. Otherwise, if we say further than, and we click on that button, the tool is going to assume that it's going to be anything that is further than 500 meters to 5,000 meters. And then it's going to select to create the filter and the mask, sorry. So this is how the distance mask would look like. In this case, it was a protective distance mask in the same area in the Ardennes, and the filters were selected to be 150 meters from crops, roads, and urban areas. And this is how the enhanced classification would look like, filtered by the distance. In this case, we don't see any above, any marginal land above in the green area because that's a protected area. So then in protected areas, we shouldn't have marginal lands. And finally, we have the carbon analysis tools. When we have defined this enhanced and when we have defined the area that we want to forest or reforest, we can perform 3 types of analysis. We can calculate the carbon that we may have in this area using biomass equations defined by Forrester et al. In this team, they fitted the global, universal or global biomass equations for a set of 27 species in the whole Europe, and they are generalized. So that means that they only work with diameter at breast height values, and then it will retrieve value for the whole above ground biomass. The other tool that we have is a carbon predictor. This is a little bit more interesting, and this tool, what it does is, now that we know our areas where we want to plant, we assume that if we plant 1 centimeter plant in each pixel, how the plant would grow. And this is based on a predictive DBH model defined by Shellhas, and it's combined with the biomass equations defined by Forrester and the carbon calculator. So basically, the diameter at breast height projects how the plant is going to grow in this pixel for 50 years, and then for each diameter at breast height, we get the carbon and the biomass using the equations of Forrester's. Oops, sorry. And finally, we have the forestation cost calculator, which, as they say, it says it retrieves an estimated cost of the forestation based on some, I would say, I don't know if I would say new variables, but like a slope, distance from the cities, and soil texture and labor cost. And I say new because there are some reports from the European Environment Agency that they estimate some prices for this. But as they said, they were assuming that the terrain and all the conditions were ideal, I would say, and they didn't consider some of these variables. So there might be some differences between these 2 reports, but I think that at least in here we dare to include these variables and to try to plot them. So I think that's an interesting output as well. And I would like to mention here as well that the tool that Lefter is included about the selection of a species will be helping to select the species for either the carbon calculator and the carbon predictor. So those will be included there. So how can we access this tool in general? Well, we can access through the mail app, and it's a free and open system, but there's only one limitation, that Google Earth account is required. But the good thing is it's free too, so it just requires a little bit of time creating a Google Earth account, and there's nothing else required. If you wish to get more information about our project, there's a dedicated section of tutorials on how this works in the massive online courses, which are published in our website. And here you can have a short glimpse of how our website looks like. So before wrapping up, I would like to leave you here the references for specifically the carbon tools, which were a bit more scientific in this sense. And thank you a lot for your attention. And also I would like to thank you, as Michal did, to all the developing team that helped us to create this tool.
Thank you, Miguel and Fernando, for your presentation. And I would like now to call Juan Pedro Carbonell Rivera and Jesus Toralba Perez to give the next presentation, which is about the mail massive online open course and the virtual classroom. So, Juan, you have the floor.
Thank you so much. I'm going to start to share my presentation. So let me know if you can see it.
Yeah, we can see everything.
Perfect. Perfect. So to continue with the event and before the lunch break, Jesus Torralba and I are going to carry out the presentation Mail Massive Open Online Course and Virtual Classroom. To start, we are going to answer the question, what are MOOCs, XMOOCs, and CMOOCs? Firstly, a massive open online course is an online course aimed at unlimited participation and open access via the web. The image of this slide shows the EDX website. EDX is one of the most important MOOC platforms. This platform was founded in 2012 from scientists of the IMT and Harvard University and hosts more than 3,000 courses right now. EDX is an XMOOC course platform. In the XMOOC courses, the developers are domain experts affiliated to universities and therefore create these learning platforms to reach their students and the general public. The content and structure are therefore almost the same as the traditional university delivery system, let's say, and provides certification as proof of competence acquisition. But in recent years, a new concept of course has been introduced called CMOOC. The CMOOCs has an open structure with the main objective of sharing knowledge, and it has a very important difference with the previous courses, that it is that the participants have to submit their useful suggestion to improve the course content, not having a teacher disseminating the knowledge, but a group of users sharing it with each other. During the planning of this MOOC, of the email project, we thought it was best to create an XMOOC, let's say a traditional MOOC course, to disseminate the knowledge of the experts who have participated in the mail project. UPBX is the platform of the Polytechnic University of Valencia, and UPBX is the platform where the MOOC of the mail project will be hosted first. I say first because later the MOOC will be hosted on the EDX platform, where it will have greater visibility and dissemination. The UPB is a member of the EDX consortium and is one of the first European universities regarding the number of MOOCs produced, and has developed several well-known e-learning products. The experience of the UPBX technician in the creation of MOOCs has helped us a lot, increasing the quality of our MOOC. The main objective of our MOOC, called Management of Marginal Lands and Carbon Sequestration Estimation through Remote Sensing and GIS, is to provide training, knowledge, and information about the tools, methodologies, and techniques that we develop during the implementation of the mail project. This course is addressed to foresters, surveyors, remote sensing, and GIS specialists, and also students. So let's say a bit of information about this MOOC. The total duration will be 5 weeks for a total of 5 sections. The dedication will be 4 hours per week. So in total will be 20 hours. There are only a minimum requisites, that there is to have a text processor like Word, for example, QGIS, Google Earth Engine, and RStudio. The evaluation will be a final exam in each of the sections. So at the final, the users will have to do 5 exams. And about this course, all the videos are based on the procedures followed in the mail project, and the mechanics of the course are very simple. Follow the learning sequences proposed by the platform by watching the videos and asking the questions and activities that are proposed. In some cases, the user will find optional readings that can read in order to expand the subject. And finally, to speak about the content of the course, I would like to give the floor to my colleague, Jesus Torralba. But before, with this slide, where you can see the introductory videos recorded by some of the MOOC teachers, I would also like to thank all the people who have collaborated in the MOOC for all their hard work. For example, Bettina, Samuel, and Janer from ABG, Maria, Natalia, and Harry from the University of Thessaloniki, Michał, Eva, and Marek from the CBK, Francisco, Laura, Alfonso, and Fernando from CESE4, Lamprox, Alex, Ino, and Nikos from Homeotech, and finally, Jesus and I from the UPB. So, thank you, and I think, Jesus, you can continue with your presentation.
Okay, let's go. Can you see my screen?
Yeah, we are seeing the desktop right now. Yeah, and now the presentation, perfect.
Perfect. Hello, everyone, and thank you very much, Juan Pedro, for your presentation. My name is Jesus Torralba Pérez, and I am a forest engineer and a PhD student working at the Polytechnic University of Valencia. Well, now I am going to show you the content of each MOOC section in detail and how to access it. The MOOC is divided in 5 sections, as my colleague Juan Pedro said before. In the left margin of this figure, you can see the institution that had been the leaders of each sections. The first section is organized in 6 videos in which the definition of marginal land is discussed in depth. The policies related to marginal land are reviewed, and the data set available for the characterization of marginal land are explained in detail. This section is based on the task 2.1, literature review on marginal land definition, task 2.2, collection of appropriate existing European and global data sets, task 5.1, best practice marginal land monitoring using remote sensing techniques, and task 5.4, success stories of the use of open source software, web application, and free satellite data. The second section is the longest one and has 10 videos. In this section, we explore the proposal of the identification and classification of the marginal land performed in the main projects, as Maria explained in the morning. For this section, we had prepared 4 practical videos where we process the data with the software QGIS and in the Google Earth Engine application. The most important task in this section has been task 2.3, methodology developed of marginal land detection. In the third section, we give a bibliography review of biomass estimation with remote sensing data, and especially we study the data set collected by Sentinel-1, Sentinel-2, satellites, and LiDAR data. This section has a total of 9 videos, and one of them is a practical exercise to process the LiDAR data using Fusion, LastTool, and AirStudio software. This section is based on the knowledge acquired in task 2.6, estimation of biomass volume at low productivity marginal land, and task 2.7, marginal land classification in carbon sequestration capacity groups. The fourth section shows the direct and indirect methods for carbon storage and accounting, and including an overview of Ipcc accounting rules. The section is divided into 4 videos, one of them which is a practical exercise in AirStudio. This task is based on the knowledge acquired in task 2.5, existing models, task 4.2, quantification of increased carbon sequestration capacity in marginal lands, task 4.3, estimation of carbon stock in forest products, and task 5.3, stock exchange marker for carbon reception. And then the last section is the section 5, and we present how to use the web portal created in Google Earth Engine to manage the marginal lands. Specifically, we explain each of the identification and classification tools, such as the carbon calculation tool or the carbon predictor, and the decision support system. This session has 5 videos and is based on task 2.9, web application for the management of marginal land biomass, and task 3.4, accompanying software system. As Juan Pedro said before, in addition to the videos, you will have questions for self-evaluation after each video. You have a weekly practice, and at the end of the course, you have an exam where you will be asked about the content of whole MOOC. The course will be considered passed if the final score is equal or higher to 50% of the maximum possibility grade. And finally, I'd like to invite you to participate in the MOOC, which will be online on the UPBX platform from the last week of December. And to access to the MOOC, the only thing you will have to do is search the UPBX register. You need to register in the application as an user. This is free, this is open, and then you only need to search for the main MOOC within all the courses offered by the UPB. Right now, we are uploading some videos, adapting the subtitle, and finishing the training questions and the final exam questions. We will keep you informed through our social media, Facebook, Twitter, of the launch of the MOOC, sorry. Thank you very much for the attention, and it is all.
Thank you, Juan and Jesus, for the presentation of the mail MOOC.